In this video, you'll learn how to model 1 degree of freedom rigid body motion in a transient fluid simulation using ANSYS Fluent's 6 degrees of freedom solver. This solver allows you to account for external forces and moments exerted on a moving body by the flow, and its 1 DOF settings allow you to easily include spring forces and limits to the range of motion. This approach can be used in modeling flow-driven motion of spring-loaded valves. This demonstration uses a simple mock-up of a pump with a single piston and 2 check valves, inlet and outlet. I've already defined this case as a transient turbulent flow for a compressible fluid. I've also defined inlet pressure and outlet pressure boundary conditions and set up mesh interfaces between the moving piston and fluid chamber adjacent zones. Let me display the mesh on the plane at z = 0 and also on the faces of the piston and inlet and outlet check valves. The computational domain consists of several zones. This region, meshed with hexes, is where the piston moves up and down. The mesh will be updated using the layering method. The motion of the inlet and outlet check valve zones will be modeled as 1 DOF translations. The mesh deformation in the fluid chamber due to the check valve's motion will be modeled using smoothing and remeshing. Note that when the check valves are in their most closed positions, as shown here, I will maintain a gap of a single layer of fluid cells between the valves and the fluid chamber walls so that I do not have to account for the change in topology that would result from actual contact. Now I'll enable the dynamic mesh option, select all mesh methods, and specify their settings. For smoothing, I'll keep the default settings. For layering, I'll select the ratio-based split option, which must be used for faces that are not planar. For remeshing, I'll select local cell and local faces, and specify the mesh parameters based on the mesh scale info that reports the minimum and maximum sizing for the entire domain. If these criteria are not met, Fluent will remesh the zone. To account for the motion of the check valves caused by the pressure forces, I'll enable the 6 DOF solver. First, I'll define a set of properties for the inlet check valve. Because the valve is moving in a single direction only without rotation, I can enable 1 DOF translation. I'll specify the total mass of the valve and define a direction vector. To model a Hooke's law spring acting on the valve, I'll specify the stiffness constant. I could also define a negative or positive preload on the spring to specify that it is already deformed, that is, stretched or compressed, at the initial position of the valve. A positive preload would result in a force being applied in the defined positive direction. To limit the range of motion of the valve along the direction vector, I'll enable constrained, and then I'll assign a location value to the valve in its initial position. I can enter any number, whatever is most convenient for the case. This number, along with the provided direction, establishes the local coordinate frame in which the minimum and maximum values are specified. In this case, the valve is initially located at the origin of the local coordinate frame and can only move 1 millimeter in the positive direction. When I create the set of properties, it appears under the 6 DOF properties. Similarly, I'll define a set of properties for the outlet valve. Note that every independently moving body needs its own set of properties with a unique name, even if they are identical to another body's properties. During the run, I want the Fluent solver to write the history of the location and orientation of the 6 DOF dynamic objects at every time step. Now I'll create dynamic mesh zones and specify their motions. The wall piston zone will be moving as a rigid body, and layering will be used to define the mesh deformation. To define the velocity of the zone, I'll use a UDF that represents velocity as a simple sine wave function. Since I've already compiled and loaded the UDF, I can select it. I'll specify the initial center of gravity location and keep the default rigid body orientation. For dynamic layering zones, you must specify the cell height correctly. This value controls the expanding and collapsing of the mesh layers. The next zone is wall inlet check, which will also undergo rigid body motion. I'll enable 6 DOF and prescribe the inlet check motion set of properties that I created earlier for this zone. I won't enable passive because I want the forces on this zone to affect its motion. I'll also specify the center of gravity location. In a similar manner, I'll create the wall outlet check dynamic mesh zone. Finally, for the fluid chamber zone, the mesh deformation will be controlled by smoothing and remeshing. I also need to adjust the local zone parameters that will be used as remeshing criteria. At this point, the dynamic mesh case is set up. Lastly, I've created surface report definitions for monitoring the integral of pressure on the inlet and outlet check valves, and mass flow rate at the inlet and outlet. For deforming mesh problems, it is also recommended to monitor maximum cell skewness in deforming zones. High skewness values indicate large mesh deformation. To summarize, I'll show you the report plots that I've obtained during the solution run. This is a history plot of the mass flow rates at the inlet in white and at the outlet in red. And this is a plot of the transient force profiles. The white and red graphs represent the integral pressure forces on the inlet and outlet check valves, respectively. And here's a quick look at animations of pressure contours due to the motions of the piston and check valves. Here you can see the pressure variations on the inlet side. And this animation shows pressure variations on the outlet side. This concludes the demonstration of using the 6 DOF solver in dynamic mesh simulations in ANSYS Fluent.